Okay, number 6, stationary zone. We have features close it. Okay. The length of the, let's read the question. Always yep, the graph show after 2. Okay, so the oh, I think it's cancelled question. Number 7. A vertical tube is partially filled with water. A sound wave moves down the tube and it's reflected by the surface of water. The frequency of the sound wave is gradually increased from 0 until much louder sound is heard. Okay, water is then removed from the tube until the second loud. So the frequency sound wave moves down the tube and it's reflected by the surface of the water. So we have from 0 until much louder sound is heard. So we have first stationary wave. We have the first loop, the fundamental loop. So the open, recall again, where the particle which at the open tube are displaced to the maximum. So we draw antinode here. And this at the boundary at the surface of water act as the boundary of column air in this tube. The particle air in these boundaries are not displayed so it's not here. Then we draw our first fundamental loop of the stationary wave. It's a half of wavelength, so it's just a quarter part of wavelength. Yeah, and it's reflected. So what's happening to the particle uh, in this sound wave? What's actually happened? See to this picture. What's actually happened to the air and the sound on the tube here? Okay, so when the sound is produced here, yeah, so this sound is using tuning fork, but you can use, instead of tuning fork, you can use speaker or other sound source, yeah, to create a sound here. So when the sound is produced here, it displays the particle air. It displays the particle at the open particle here. Okay, you can see that this particle is displaced. Yeah. Look at to the first row of the particle. It's displaced to the maximum of the displacement, and look at to the particle which lay on the boundary. It can't go anywhere. Yeah, the particles can't go anywhere, so this place is referred to the node part. This is the first fundamental particle stationary wave. So what happened to the next stationary wave? Okay, you see here the particle at open tube is still displaced to the maximum, but this is not, yeah, the particle which at rest, yeah, because it pressed the two, but it's pressed by two direction here. So some particle here are at rest, or the particle here is referred to node. Yeah. Okay, back to the question. The water is then removed from the tube until the second loader sound is at, which diagram show the new pattern of stationary wave that's formed. Okay, first we have our fundamental stationary wave, and then when the water remove, yeah, it gives a space of air to move here. So we already have a half, sorry, we already have a quarter of length. So to remove example to here, the water, yeah, what's gonna happen? Yeah, it creates stationary wave here because the air, because it fills by the air, and then the air is moving because the sound produced, yeah, it produced by the sound, and it creates stationary wave. So this is the water, the new surface of the water, and the water and the particles lay on the surface here are not, can't go anywhere, and then it's referred to node part. So this is node, so this is node, the first node we draw here. So just connecting the connecting by the wave line. Okay, we continue here. Sorry, yeah, and then here we go, we have the second stationary wave. Yeah, it refers to the second loader, and then if the third loader, you just add third loader, the water will decrease again, and then it will create another loop. Which diagram show the new pattern of stationary wave that's formed? Okay, they look same like this diagram is C. Okay, okay, analyze the picture here. Each load at half of wave, yeah, at half of wave. So it's a note that when the frequency of stationary wave is 8, or the loader is 8 to the third loader, uh, the part of stationary wave is at half wavelength. Number 8, wire is fixed at both ends and it's vibrated by sun. Okay. A stationary wave is formed on the wire with a total of two antinodes. Two antinodes. Okay, two antinodes. Okay, we draw the first antinode. Yes, so this is the first antinode. So the second antinode. So this is the second antinode. So this is F. So how about 3F? 3F. So uh, you just add triple of this diagram. 1, 2. It's too big. It's too big. Oh. We draw We draw here. So this is the first frequency. Yeah, refer to the question when the first frequency from 2 NT note. To NT note, this is F, and then it's increased to 3F, and then we make a triple of this diagram. 1, 2, I'm sorry, we double it. So this is the 2F, and this is the 3F. So how many NT note we have? 1, 2, 3, 4, 5, 6. We have 6 NT note. Next, a loudspeaker emitting a sound wave of single frequency is placed a distance L from reflecting a sound. A stationary wave is formed with NT note at the loudspeaker. Yeah, so this is okay. It formed an NT note at the loudspeaker. A microphone is moved from the loudspeaker to the reflector because before the microphone reach reflector, it detects 4 points where the sound intensity is minimum. We have four sound intensity is minimum. Is minimum. It refers to note. So we have 4 note before it reach the reflector. So the reflector also, the particle at reflector also note, and then we have, this is 1 note plus 4, and then we have 5 notes here. Okay, we divide it equally as we can. So this is NT note 1, I think 2, 3, 4, this is 5, 2, oh, I'm sorry. We can draw here. Two note, 3 note, 4 note, 5 note. What if the wavelength of the sound wave? So in this L, in this length of the tube, it creates one. So it begins from this, start from the NT note, and then NT note to the next and the third loop. Okay, so this is one wavelength, and here our 2 wavelength, and it left quarter wavelength. So we have 2 full wavelength and 1 4 wavelength. Yeah, plus So it's equal to 9 per 4 wavelength. So we have 9 per 4 wavelength. And then what is the wavelength of the sun? So the wavelength is equal to, we just do a simple mathematical operation. So we switch 4 per 9 L. Answer is C. A corridor is 13.2 meter long, has closed door that reflects sound at both ends. The speed of sound in the air in the corridor is 330 meter second. What is the lowest frequency of sound that could create stationary wave in the corridor with note halfway along it? So this is a note. So we and the particle at the closed door, it's form a note. We just connecting this knot by drawing a wave line. Yeah. So we have one wave line here. Okay, so how much the frequency? One wavelength in this tree is 13.2. Yeah, so the wavelength is equals to 13.2. So the frequency is, remember the general speed wave equation, v equals to lambda times frequency, where frequency equals to v per lambda, and v is per, okay, how much? Wait. Okay, the answer is 25. C. With notes, so you just follow the instruction in the question, that the question inform us that not halfway along it, so you're just connecting a draw line, and that's the lowest frequency of the corridor can be of the corridor that can be happen.